Howdy everyone, welcome back for Chapter 8, Basic Concepts of Chemical Bonding. So this is where we'll talk about both ionic compounds and covalent compounds, what makes them compounds. When we say these atoms are chemically bonded together, how are they bonded together? What's holding them together? What's the energy like for that? So we'll look at all those things. So it's, again, a kind of light on math chapter, but it is a lot of definitions, and there are a couple kind of processes where you got to say, okay, let me do this step by step. But the nice part is if you follow the steps correctly, you will get the right answer every time. So let's learn those steps as we get to them. All right, so chemical bonds, we got three main types. We have ionic bonds, where we have the positive and the negative opposites attract. We have covalent bonds, where electrons get shared between atoms. And then we get metallic bonds, where electrons that can kind of float between atoms, and because they can go back and forth between lots of atoms at the same time, they're all held together. It's called the sea of electrons, and that's about all we're going to talk about that right now. Okay, Lewis symbols. These were developed by G.N. Lewis back in the early 1900s, trying to explain why is it that we get certain compounds, certain formulas, but not others, depending on what the element is. And so he had this idea of using just the valence electrons and representing them as dots around the element symbol. I know when he did his actual work, more complicated, he actually did like cubes around the symbol. He was trying to draw in 3 dimensions and saying, oh, the dots go on the corners of the cube. But it works out because the idea is we still want to get 8 electrons. So a cube has 8 corners. We're going to do 4 sides with pairs. But the idea being atoms will tend to gain, lose, or share electrons to get to 8 valence electrons. That's what we call the octet rule. 8 tends to be stable, just like the noble gases. Neon and argon here you see have 8, 2 on each side. So the rule for these Lewis dot diagrams, these Lewis symbols, you put the element symbol in the middle. You then put 1 dot on any side. The first 4 dots get spread out among kind of 4, if you imagine an invisible box around the symbol, 1 on each side. And then when you get past 4 valence electrons, you start pairing them up. So here's 5 where we have 1, 2, 3, and then a pair. 6 has 2 pairs and 2 singles, 7 and 8. So we have 4 sides, 1 do a side first, and then pair them up as you have to. Kind of like we did with Hund's rule with the electron configuration. Spread them out if you can, pair them up when you have to. All right, so for ionic bonding, this is where we have metals and nonmetals. This also applies to polyatomic ions, but we're going to focus on just nonmetal anions for right now. It's electron transfer. The metal is losing the electron. The nonmetal is gaining the electron. And the overall process of switching those electrons between them and forming an ionic solid is extremely exothermic. That's why it happens so much. The idea here, if we look at this reaction and we use the Lewis symbols, the sodium had 1 valence electron, the chlorine had 7. That electron is moving from sodium to chlorine to form a sodium ion and a chloride ion. So this is how this is diagrammed with Lewis symbols. And overall, that's a very exothermic, a very energetically favorable process. All right. Well, how do we know it's an ionic solid? What are those properties? We talked in the last chapter about the properties of metals, the properties of nonmetals. What about the properties of ionic compounds? Well, because they are a 3-dimensional crystal held together with opposites attracting, they tend to be brittle. Because you can imagine kind of just separating a line, and there's a nice clean line that you can break at. So they tend to be a bit brittle. They have very high melting points. They're very attracted to each other. So in order to get them to move around as a liquid, you've got to put a ton of energy in to make that happen. They are crystalline. That means it's an ordered arrangement. It's the same thing in all 3 dimensions, just repeating over and over. And so then, like I said earlier, they can cleave along smooth lines because we have kind of planes of where does one layer end and where the next layer begins. And you can see here, if you look at that picture and imagine looking on the inside, every sodium would be surrounded by 6 chlorides. Every chloride would be surrounded by 6 sodiums. And take a moment here on this picture, pause the video, try to figure out how can we know it without this label? How would we know that the purple one was sodium and the green one was chloride if they weren't labeled? Okay, and the answer is going back to chapter 7 with ionic radii. Cations will lose electrons and get smaller. Anions will gain electrons and get bigger. So since sodium and chloride are around the same row, they're going to start in the same ballpark, but sodium will get smaller, so it should be the smaller purple one. Chloride's going to get bigger, it'll be the larger green one. And there have been AP free response questions like that where they give you a diagram, and one of the questions is label which one is which. So knowing your ionic radii is going to help you out there. All right. Why is forming an ionic compound so favorable? I mentioned this in chapter 7, that it's the overall process. Well, here is that overall process. It's called the Born-Haber cycle, where we start with the elements. So we're starting at this line here. We are going to make some gaseous atoms, because officially reactions happen in the gas phase. So we turn the sodium solid into a gas. There's a delta H for that. We then have to split any bonds that are already formed. So chlorine is diatomic, it's Cl2. We have to split that into just Cl, and that's a delta H, and it's endothermic. We've got to remove an electron from the sodium. That's endothermic, so up in energy again for that ionization energy. Then we've got to add the electron to chlorine, and if you go back to chapter 7, you'll see, oh, that first electron affinity for chlorine, that's exothermic. So we come down a little bit in energy. And then we get the big one. What happens when we take these two gaseous ions and combine them into solid sodium chloride? And that is incredibly exothermic. That's the part that releases all the energy, because you've got all these positive sodiums and all these negative chlorides, opposites attracting, and it forms a very stable solid that releases all that energy. Now, the reason we call this a cycle is because you can say, well, hey, wait a minute. If I add up all these steps, then the difference here is going to be the heat of formation for sodium chloride. That going from the elements to the finished compound. Hey, that's heat of formation. So that's that missing gap. And so if we know all these others, we can find the delta H of formation. What's normally done is actually we can measure that through calorimetry. We can actually measure these through calorimetry. It's this lattice energy that we're going to use Hess's law to say, hey, if I know all these other values, what's the missing step? Let's get that lattice energy. All right. So if we kind of talked through this in the previous slide, it took energy to convert the elements to atoms, took energy to create cations, to get them in the gas phase. We got energy out from making an anion, but it's the huge amount of energy from the formation of solid that makes the whole thing exothermic. All right. Now a little bit about that lattice energy. If you go back, rewind the video a little bit, you'll notice it said negative lattice energy on that figure. That is because the definition of lattice energy is the energy required to separate the solid back into the gaseous ions, which is kind of weird because that's not what happens, right? We always take the ions and form the solid. It's just the way that we decided to define things. So lattice energy is the energy to separate the lattice. So then that amount of energy is released when we make the solid. And so they say here, okay, the lattice energy for sodium chloride to make the gaseous ions is positive 88 kilojoules per mole. So then when we form the solid from those gaseous ions, it'll be negative 788 kilojoules. That much will be released. So just watch out for that. It's a weird definition thing, but lattice energy is always positive by definition. We have a definition at the end of the chapter that's the same thing for bond enthalpies. They are always positive, just by definition. All right, and here are some examples. So we can see for lithium, as we go from fluoride to iodide, it drops. For sodium, from fluoride to iodide, it drops. I'm not sure why they skipped to lithium bromide. It's dropping as we go down from fluoride to chloride to bromide. It's always dropping. But then, hey, look at these where it's +2 ions. With magnesium chloride and strontium chloride, over 2,000 compared to sodium chloride, 788, lithium chloride, 834. This doubles or triples. And then, hey, what if it's +2 and -2? Suddenly we're in the upper 3,000s. And then scandium nitride, a +3, -3 ion, or ions in that compound. We're over 7,000 kilojoules per mole. So what trends can we get from this table? Well, there's two trends, and it's all about this equation that we already looked at back in chapter 5. That's what said when we have electrostatic attraction, What matters are the two things. What are the charges and how far apart are they? So it says here, lattice energy increases when we have increasing charge. And sadly, they don't give us a figure here, but we can see that right here. When it's +1, -1, in the hundreds, maybe right around 1,000. When it's +2 and -1, okay, now we're up to 2,000s. +2, +2, 3,000s. +3, -3, 7,000s. So the more charge there is here in the numerator, we get a bigger lattice energy. The distance also matters. We get more lattice energy with smaller ions. So here, see with lithium chloride, where lithium's the smallest, all of these are chlorides, the lithium's the smallest, bigger lattice energy because the denominator will be smaller. As we get to bigger and bigger ions, like cesium here, well, cesium's the biggest of them all. It has a lower lattice energy because the denominator is getting bigger. And it doesn't matter if it's cation or anion, same thing. These are all sodium, so that part's equal. As we go to bigger anions like iodide, the lattice energy also decreases. So this is also a very common question on the AP test, especially in the free response. They'll say, oh, here's lithium chloride versus magnesium oxide, something like that. Why is the delta H for magnesium oxide so much bigger? And you say, oh, well, the distances are about the same, but then the charges for magnesium oxide are much bigger, so it's more energy. All right. Sometimes it'll be like even lithium chloride versus rubidium chloride. So they'll say, hey, the chloride's the same. That makes it easier. So you say, oh, well, then it's all about the radius. All right, for ions, we talked a little bit about this in earlier chapters, but just to kind of reinforce, the main group metals will lose electrons. They form their cations. They go back to the previous noble gas. Nonmetals are going to gain electrons to get to the next noble gas and fill in the missing p orbital spots. Transition metals tend to not follow the octet rule. Some of them do, like titanium often is +4. Well, that follows the octet rule. It goes back to the noble gas. But sometimes, like chromium is a +2 ion. And you say, hey, wait a minute, that leaves you with a bunch of d electrons. That's not 8. That's not what's going on there. Transition metals, just don't worry about the octet rule for them. They will lose the 4s electrons first. That's what they mean here by the valence. Then they'll lose d electrons if you've removed enough electrons for that. As I say, if you need to for the necessary given charge. All right, that was ionic bonding. Now let's talk about covalent. So for covalent, we're sharing electrons. And the idea is, okay, we have the nucleus of one atom being attracted to its own electrons, but also to the electrons of another atom. And then the other atom can be attracted to both of those sets of electrons. But then the two nuclei, they don't want to get too close because then they'd start to repel each other. And the electrons still need to spread out some, or else they'll get too close to each other. So there's this balance between sharing electrons to get more attraction that way, but not getting too close, because then you get too much repulsion. And so here's a picture where we have an electron density cloud to show you, like, okay, here's one atom, and you can kind of see the spherical shape around it. And here's another atom with kind of the spherical shape. But there's a good amount of shared density in between. And that's the attraction between this nucleus and maybe some of the electrons that actually came from that atom. And so they say for a bond to form, the attractions you get must be greater than the repulsions you have to put up with. So if it doesn't work out and we say, hey, nope, too much repulsion, you just don't get a bond. This is going to come up in a later chapter that we're just not going to be dealing with. Lewis structures. How are we going to diagram these covalent bonds? How are we going to show the sharing? So we're going to take those Lewis dot diagrams that we had before and combine them to say this is what's being shared between atoms. So we start off trying to give every atom an octet if it needs it, or at least to complete the row. So hydrogen is an exception to the octet rule. It only wants 2 electrons because in that first row it's just 1s1 and then 1s2. 2 is your maximum. So if we share 1 electron from the hydrogen there and 1 electron from this hydrogen here, if they're shared, That gives each hydrogen the 2 electrons it's looking for. That's a stable covalent bond. For chlorine, each one had 7. So there was a 7th dot here for chlorine. For that one on the left, there was a 7th dot here for the chlorine on the right. They're being shared, represented here by the line as the bond. Now each chlorine can say, oh, I've got 2, 4, 6, 8. There's my octet. 2, 4, 6, 8. There's my octet. So the trick here with Lewis structures, we can double count the electrons in the bond. That's why people didn't like Lewis structures at first. They said, G.N. Lewis, you're kind of weird with how you're double counting electrons. How can you do that? And he said, but it works. And eventually people said, hey, it does really work well. Let's go with it. So when you're sharing electrons, you do get to double count them. All right. Well, then if we go to more complicated stuff, what about ones where there's more than one bond? We're still looking at how many bonds do we need to get that stable octet. So here for water, why is it H2O and not just OH or H4O or something else? Well, because when we have 2 waters, that's how oxygen can get an octet. 2, 4, 6, 8. For nitrogen, why is ammonia NH3? Because if we form those 3 bonds, the nitrogen gets 2, 4, 6, 8. So you can see, why are these, increasing number of bonds or whatever they're doing? It's to get 8. There are exceptions that we'll talk about later, but right now 8 is our goal. All right. When we draw these structures, we talk about the electrons a little bit differently. We say lone pairs are the electrons that are only on one atom. So that would be these 2 pairs, like there's a lone pair, there's a lone pair, there's a lone pair, there's 3 lone pairs. And then the bonding pairs, well, these are the shared ones. They're the line in between. They can also be represented by 2 dots. We just put 2 dots in between. I prefer the lines because it's much cleaner, but never, ever, ever do both at the same time, because then it's like, well, wait, what's going on here? Is that 2 pairs? Is it 1 pair? Did you forget to erase? No one knows what you're trying to do. Don't do both. So here on this last picture, there's a bonding pair. Here we have 2 bonding pairs. We have 3 bonding pairs. And here we have 4 bonding pairs. Sometimes you get a multiple choice question that'll be, in the Lewis structure for this compound, how many bonding pairs and non-bonding pairs or lone pairs are there respectively? And so for water, you'd say, oh, there's 2 bonding and 2 non-bonding, 2 lone. For ammonia, 3 bonding and 1 lone. For methane, 4 bonding. Okay, so sometimes you get a nice, easy multiple choice question like that. You just have to know, what does the picture look like? All right, for multiple bonds, sometimes we need to share more than just that pair of electrons to get to the octet. Sometimes we need 2 pairs, and we call that a double bond. Sometimes we need 3 pairs. We call that a triple bond. So here's a picture of carbon dioxide where we need 2 double bonds, but by doing that, we can see around the carbon, 2, 4, 6, 8 around the carbon. Here for dinitrogen, the nitrogen in the air, it has a triple bond because we need 2, 4, 6, 8 in order to get that octet. All right. We will be talking about in the next video, well, how am I getting these pictures? Where did they come from? Right now, we're going to focus on just what are the parts of these pictures called, what do they tell us? Then in the second half, how do we draw them ourselves? All right. These bonds, when we're sharing electrons, we don't always share them equally. It's kind of like if you have a teenager and a toddler in the same household, they are not going to eat the same amount of food. Not everybody gets the same scoop. So bond polarity is how we say how equally shared is it. If something is considered non-polar, they're shared equally or very nearly equally. In a polar covalent bond, one of the atoms is pulling the electrons towards itself more strongly than the other one, so the electrons spend more time on that half of the bond. And we'll figure out how do we get that. All right. So here's a couple examples using fluorine. In elemental, F2, because it's fluorine versus fluorine, we've got a tug of war going on between identical twins. It's evenly split. So you can see here kind of greens in the middle, green and yellow. So hey, it's evenly split between the 2 fluorines. But if we have hydrogen fluoride, where fluorine can pull more strongly than hydrogen, we see, hey, there's red over here on the fluorine side. That's more negative because more electrons that are negative are spending time there. The hydrogen side is more blue. It's more positive because the electrons are spending less time there. If we go all the way to lithium fluoride, where we'd say, hey, that's basically ionic, you can see, hey, it's basically completely negative on the fluorine side. It's completely positive on the lithium side because we'd have a lithium +1 and a fluoride -1. So that makes sense there. Right, so that's about the bigger the difference between the two atoms, the more polarity you're going to have. Right, how do we know how big the difference is? We use electronegativity. So this is another periodic trend. We just didn't talk about it in chapter 7. But you can see here, it tends to increase as we go left to right. So the higher numbers are here on the right side, lower numbers at the left side. So yeah, higher at the right side, lower at the left side. It also tends to be a bigger electronegativity at the top of the column and then lower as you go down. So fluorine's in that top right corner, it's the highest, 4.0. Cesium's in the bottom left corner, it's the lowest, 0.7. And so the gap between those two numbers will tell us what type of bond are we getting, how polar is this bond. Right? So when it's equally shared, it's a non-polar bond. When it's unequally shared, we say it's polar. Usually it needs to be at least 0.5 or so for the electronegativity difference to be considered polar. Because then, like we said, electrons will spend more time at the more electronegative atom. That gives it a partial negative charge. It's not completely negative, it's partially negative. That's represented by a delta minus. That's a lowercase delta, so delta minus, partially negative. The other atom is a little bit positive, partially positive, so delta plus there. So we can draw it this way, where we'd have, okay, here's our hydrogen fluoride. We said the fluorine was partially negative, so there's the delta minus. The hydrogen had some plus to it, so it's partially plus, delta plus. Or we could use this extra arrow, where we draw an arrow heading towards the fluorine, and we put that little bar at the bottom. That's saying, hey, the electrons are being pulled to the right-hand side. That's what that symbol means. So these are kind of interchangeable. This is showing us what's called a dipole moment, which we'll get to in about a slide or two. All right, so the greater the difference, the more polar the bond. So here for hydrogen fluoride, huge difference, very large dipole moment. You see a big difference in the plus versus minus. As the difference gets smaller, then the separation gets smaller. So HCl, still pretty polar there. HBr, not as much. HI, oh, that's only a dipole moment of about 0.44, only a small difference. Not all that much going on there. So this one's going to be much less polar. Right. Well, how do we know how big that dipole moment is? Which, given the symbol mu, you don't need that for the AP test. You need to know that it's a dipole moment. And that it's going to depend on what's the charge, which is basically what's the partial plus and partial minus, and the separation, the radius, the distance. So it's how far apart are they, what's the charge. So the bigger the electronegativity difference, we'll get a bigger separation there. And then if they're farther apart from each other, you'll also get a larger dipole moment. So a longer bond can give you a larger dipole moment. Right? But what you need to focus on is if I have a bigger electronegativity difference, that's where I'm going to get this bigger dipole. All right, last thing before we move on to the next video, how do we tell if something's ionic or covalent? The simple approach is saying, oh, metal and nonmetal, ionic. Non-metal and nonmetal, probably covalent. There are some exceptions. Some metal with nonmetal compounds can be better treated as covalent, depending on their properties. The better way I like to do is look at electronegativity difference. But again, they say, hey, that doesn't always take account an oxidation number for some of those transition metals. And so the best way of saying it is the properties. Ionic compounds are going to have high melting points. They're going to be electrolytes. They're going to have the brittle solids. That means ionic. If you have a lower melting point, if it's a non-electrolyte, that's going to point you towards covalent. So if you're given properties, go off of them. If you don't have properties, maybe look at electronegativity, and then if you have to, just look at the formula. All right? So that's what we're going to stop for part one. Part two is going to be all about how do we write Lewis structures, which will probably be review from Chem 1 for a lot of students. But then we're going to add some new stuff in to say, okay, if we've got more than one possible Lewis structure, how do we figure out which one's the best? And that's where we can get some tricky stuff. So join me for that in a day or two or whenever you watch this video.